All right, welcome everybody. So in this video, we are going to more generally define what a Markov chain is. And as I noted, that these Markov chains, they have applications throughout tons of really interesting, diverse fields. So they have applications in statistics, probability, and machine learning, as well as outside of mathematics and statistics in biology, finance, and epidemiology. So informally, a Markov chain is a type of mathematical model that is used to describe an experiment. So I use the word experiment a little bit more loosely than you may be used to applying this. So for example, we can think of the weather as an experiment and that there's two possible outcomes that we can get, and each of those outcomes has a certain probability of occurring. And so we're going to repeat this experiment repeatedly under the same conditions. So in other words, the probabilities don't change. If it's sunny today, there's always a 90% chance that it's going to be sunny tomorrow. And for each of these experiments, we have a fixed number of possible outcomes. We have n possible outcomes, and those possible outcomes are the same at every possible time. So in our example for the weather, we had two possible outcomes. There is a set of probabilistic rules that describes how the system transitions from one state to the next, and those probabilities depend only on the current state. So in other words, whether or not it's sunny tomorrow only depends on whether or not it's sunny or raining today, and we're not going to take into account any other factors. Okay, so now let's define a Markov chain more formally. So a Markov chain is a sequence of vectors, x1, x2, x3, that we call state vectors. So x1 is going to tell us what the initial state of the system is. x1 is going to tell us what the state of the system is after one time step, and so on. So each of these vectors is going to sit in Rn, where n is denoting the number of states that this system has. So along with these state vectors, we have a stochastic matrix, which happens to be the transition matrix of this model that we often denote P. So P contains all of the probabilities that if I know what the current state is today, what are the probabilities that we're going to be in state 1, 2, 3, 4, etc. tomorrow. So in order to figure out what the state is at the next timestamp, this is an iterative process. All I need to know is what is the current state and what is the transition matrix. So I get the next state by multiplying the current state vector by the transition matrix. And then to figure out what state 2 is, I would multiply state 1 by the probability vector. So in general, if I want to figure out what is the state of the system at time k plus 1, then what I would do is take the state of the system at time k and multiply it by this matrix P, where here we're thinking of k as 0, 1, 2, 3 non-negative integers. And so if we continue looking at this weather model where we had two conditions, sunny or rainy, with these probabilities, we set up the transition matrix P, which has the first column 0.9, 0.1, and second column 0.5, 0.5. And if in addition we know that today the weather is sunny, well then this would give me an initial state vector which says has first entry 1 and second entry 0, meaning currently we're in state 1, which is weather. And now let's say I want to make a prediction for what is the weather going to be 3 days from now. Let's see how that would go. So that's going to be x3, and we do not know what this value is. But I know how to find it if I know what x2 is. So I would take the state in x2 and multiply it by this probability matrix, the transition matrix. Well, I don't know what x2 is just yet, but I do know that x2 we find by applying the transition matrix to state x1. And again, I don't know what state x1 is, but I know that I can find x1 by multiplying x0 by p. So we can see if I want to make a prediction for the weather, for the state of this system, 3 days out, 3 time steps out, then I'm going to multiply the initial state by the transition vector 3 times. So it's going to be really convenient to find some nice ways of exponentiating these matrices, which we have seen in the case for matrices, for example, that can be diagonalized. So here we would multiply this vector 1, 0 by the vector p 3 times, and I will save you the calculation. There's a link to a Google Colab document where I'll do these calculations. That comes out to a vector where the first entry is 0.844 and the second entry is 0.156. So this first entry tells me that 3 days from now, there's an 84.4% chance that it's going to be sunny and a 15.6% chance that it's going to be rainy. And notice what comes out is another probability vector. So this adds up to a probability of 1.